Now we're going to get back to our conversation about area under the curve, and we're going to try to return to that original question that we had in the last video, which is, well, okay, we can sometimes find the area under the curve really easily if that area happens to be a triangle or a circle or some other nice shape that we actually just know the formula of the area for. But for most functions that we look at, we don't have a nice formula, right? If you have some sort of a curve, right, we don't have necessarily right off the bat, we don't have a formula to tell us, you know, the shape of this area here, for example, right? If we wanted to find the area between this curve and the x-axis over this interval here, right, this interval here, well, what the heck kind of shape is that? I don't even know what you would call that. And so you might try to break this up into shapes that you know the area of, like maybe turn this into sort of something triangular-ish, maybe do like a large rectangle down here, another triangle up here, and try to add it up. And you might get an okay estimate, but the problem with that is you can't really scale that up and generalize it to any particular function. And also you can't really do it unless you have the graph of the function right in front of you. So we want some sort of nice way of estimating the area under the curve. That can work just sort of for any function. And so we're not going to use a particular graph here, or we'll look at this graph as an example, but we're going to come up with a method that could be generalized to other graphs as well. And so this is a technique that we call Riemann sums. So the idea with Riemann sums is that we try and estimate the area under the curve using some shape we know the area formula for, and in particular we're going to focus on rectangles. Right, so here's one thing that I could do, one way that I could try to estimate this area. I could say, well, I'm looking at this interval here from 0 to 3. The x-axis is already kind of nicely broken up into these little 3 pieces here. I didn't draw this particularly well scaled. These should all be the same length, right? 0 to 1, 1 to 2, 2 to 3. And so I'm going to break this up into 3 rectangles. And I'm going to use, right, for each one of these little intervals here, I'm going to use the right endpoint of the interval, so this one, to tell me exactly how high my rectangle should be. Right, the output of the function at 1 is up here at 5, so my first rectangle is going to have a height of 5. So I'm going to find the area of this box here. Right, then for my second interval, I'm going to use the right endpoint again of 2 to determine the height of my second rectangle. Right, the output at 2 is 4 because you have the point 24 here. So I'm going to draw another rectangle that has a height of 4. Right, here's my second rectangle. And for this third interval from 2 to 3, I'm going to use this right endpoint. F of 3 is 6, so I'm going to draw a rectangle that has a height of 6. Oof, this is going over the curve. This is not great, but okay, right? Remember, we're just trying to get an estimate of the area under the curve here. And I have to highlight this part that's above the curve because I'm using my right endpoints here to determine the height of the box. And it just so happens that this box that I'm using as an estimate doesn't entirely fit underneath the curve the way the first 2 did. That's almost okay though, because my first 2 boxes fit nicely underneath the curve, but they ended up leaving out some area. So if I add up the area of these 3 boxes, I will have missed this area here, and I will have missed this area here, but then I've added in some extra area over here, and maybe they roughly sort of cancel each other out. Right, but what we can do here is we can say, well, these boxes, because they have this sort of uniform base, where the base of each box has a length of 2, has a length of 1, 0 to 1, 1 to 2, 2 to 3, right? Each one of these rectangles has a base of length 1, okay? And so the area total is going to be, for the first box, it's a base of 1 times a height of 5. For the second box, it's a base of 1 times a height of 4. And for the third box, it's a base of 1 times a height of 6. So this area ends up being 5 plus 4 plus 6, or 15. I don't know right now whether or not that's really a good estimate or not, but it seems roughly okay. Okay, but it was sort of arbitrary for us to use these right endpoints of the interval to determine the height of the boxes. And so it's worth thinking about, would you get something different if you used the left endpoints of each interval? So we could try that too. right? So for this first interval from 0 to 1, instead of using the output at 1 to determine the height of the box, I'm going to use the left endpoint of the interval. So I'm going to use f of 0 to determine the height of my first box. So my first box is going to go all the way up to here. So I'm going to end up with this rectangle here. Okay, again, this is going to be an overestimate since I'm shading in a region that's above the curve. That's okay for now. My next interval from 1 to 2, again, I'm going to use my left endpoint here. F of 1 is equal to 5, so my next rectangle is going to have a height of 5. And I'm still sort of going above the x-axis here and overestimating the area. And finally, for this last interval from 2 to 3, I use the left endpoint. F of 2 is 4, so the height of this last box is going to be 4. All right, so for this last box, I'm underestimating the area since I end up not shading in this sort of triangular-ish region here. So I've overestimated on my first two boxes, but I've underestimated on this last box. So we hope that they sort of cancel each other out in a way. And this is going to end up giving me an area. Again, the base of each rectangle is the same. The base is always 1. And so the height really just depends on the output of the function for the left endpoint of each interval. So the height of this first box was f of 0, which was 7. So this first box has an area of 1 times 7. Second box has a base of length 1 and a height of f of 1, which is 5. And the third box has a base of length 1 and a height of f of 2, which is 4. All right, so this area ends up being 7 plus 5 plus, I said 4 and I wrote 2. It was supposed to be a 4 here. Okay, height was 4, 2 comma 4. 7 plus 5 was 4. Okay, so we end up with an area of 16, which is sort of close here, but that tells us that at least one of these is wrong, and probably both of these are wrong. Right? Probably neither of these are going to give you the exact area, but they at least give you an estimate. Now, why did we use rectangles? I mean, honestly, just because it's easy to compute the area of a rectangle, right? We probably maybe could have gotten a better estimate if we had used, for instance, trapezoids. So I drew an example here of how you could use trapezoids, right? So a trapezoid is a shape that's sort of parallel on two of its sides, but not on the other two, right? So for instance, you have this trapezoid here, but then we would need to know the area of a trapezoid formula, which is a little bit more complicated. And so the way we find the area of the trapezoid is you take, well, now the base of this trapezoid sort of been tilted on its end here. So the bases are a little bit, the bases are now kind of going up and down, and the height is along this axis. It's a little funny. And so these sort of three trapezoids take a little bit more work to find the area of them. You'd have to do this height plus this height, or this base plus this base. 7 plus 5 divided by 2 times the height, which is now going to be the part along the x-axis, which is 1. So this is 12 over 2, which is 6 times 1, which is 6. So the area of this trapezoid would be 5 plus 4 over 2 times the height, or times the base, which is 1. This is 9 over 2, which is 4.5. And this last trapezoid here, if we would try to shade this in, it'd be 4 plus 6 over 2 times the height, which is 1, so 10 over 2 is 5. So using this estimate, we'd get 6 plus 4 plus 4.5 plus 5, which gives us 11 plus, oh, look at that, gives us 15.5, which is right in between the two estimates that we got using rectangles, which suggests that maybe the actual area is somewhere between 15 and 16. Again, probably not exactly 15.5, but maybe a little bit closer. This certainly looks like a better estimate, but it's sort of a little bit more work to find the area because it's not quite as easier to find the area of trapezoids. And there's other methods people use as well to estimate this area underneath the curve. But the big takeaway here is no matter which method you use, whether you use rectangles or trapezoids or something else, you're going to get a better estimate if you use more of them. So in each case, we were using just 3 rectangles or just 3 trapezoids, but we'd get a better estimate if we broke up our interval into more than 3 pieces. For example, instead of just looking at a rectangle that has a base of 1, what if I sort of broke this down into 3 pieces on its own and did 3 separate rectangles here? Right, using the left endpoints, it would look like, here's the area of my first one, here's the area of my second one, here's the area of my third one. Okay, so I'm definitely still getting an overestimate here because of these 3 little pieces, but it's not as much as an overestimate as if I had just done one big rectangle here. Similarly, I'd want to break this one up into 3 pieces as well. So using these left endpoints, we'd have something like this, then this, and then this. And then we'd continue to use our left endpoints for the last 3 boxes that we draw. So something like this. My left endpoint here would be up here, this, and finally my left endpoint would be up here, so my last box would look like this. Okay, so I haven't shaded in all of these, but some of it's below the curve, or some of it's up above the curve, some of it comes in below and ends up missing out a little bit of area. And so it's, again, it's not going to be perfect, but it's going to be better. And we could break this up even smaller. We could say maybe break up this interval from 0 to 1 into 10 pieces and draw 10 rectangles right in between 0 and 1. 10 more between 1 and 2, 10 more between 2 and 3, and that would give you an even better estimate. Right? But the more rectangles you use, the better your estimate will be. Okay, so just to try and formalize what we're doing here, we're going to try and define what a Riemann sum is. Okay, so consider the area between a curve and the x-axis on the interval from A to B. All right, so that's what we were doing in the last example. We were looking at a curve between 0 and 3. So here our endpoints are just the general A to B. We're going to divide that interval into n even parts, and we're going to call the length of your interval delta x. Right, this triangle, we read it as delta x, and it really just means the change in x. So it's the length of your interval, b minus a, the right endpoint minus the left endpoint is the length of the interval, divided by n, divided by how many pieces you're breaking the interval into. All right, and so essentially what we're going to do here is, if this is your interval along the x-axis, it starts at a, it ends at b, and we're going to cut it up into n equal pieces. Right? The length of each one of these subintervals is going to have a length of delta x. Okay, so this is delta x units long, this is delta x units long, all the way down until your last interval, which is also delta x units long. Right? So you have all these different, you've cut this up into n many subintervals, each of length delta x. And we're going to just sort of use x0 to represent the left endpoint, which already is called A. And then each of the subintervals will just be indexed x1, then x2, all the way up until xn minus 1. And finally, the very last endpoint, which is B, we'll call that xn. All right, so with this in mind, the right-hand Riemann sum is given by this formula here. We call it R sub n. And it's given by f of x1 times delta x plus f of x2 times delta x plus f of x3, as far as you need to go up until you get to the very last endpoint, f of xn times delta x. Just to be clear what each of these represents, this represents the area of a rectangle given by the right endpoint of that interval. Right, so if this is your first subinterval from a, x0 to x1, then this is saying your first box, your first rectangle, is going to have a height that depends on f of x1, the output of the function at x1. Then we need to multiply that by delta x, which is the base of the rectangle. Right, so each one of these is representing the area of a rectangle. And this is just saying add up all those areas of the rectangles together. This is exactly what we did on the first page. right? This would be f of 1 times delta of x. The length of the interval is 1. That gave you the area of the first rectangle. This second rectangle, it had a height of f of 2, but we multiplied it by the base, which was still 1. And this last one had a height of f of 3, and we multiplied that by the base, which was 1. Okay, so it's really exactly what we were doing in that first example there. Notice though, the base of every single one of these rectangles is delta x. We get a delta x in every single one of these terms. So we could rewrite this as delta x, right? We could factor that delta x times f of x1 plus f of x2 plus f of x3, as far as we need to go up until the very last interval where we use the right endpoint here, we get f of xn. Now we have some handy notation that we use sometimes when we're adding up a bunch of terms like this, f of x1, f of x2, all the way up to f of xn. And we write that sometimes using something called summation notation, where we use this, it looks sort of like a fancy E. It's actually a Greek capital sigma, and it means sum. It means take the sum of f of x something, so we'll call this I just to say that I is a placeholder, and that I is going to range from 1 all the way up to n. So we write where I is equal to 1 at the bottom all the way up to n at the top. So this is just notation that means the same thing that we have up here. Right, so this is saying there's a sort of a quicker way of doing this, which is to just plug in the right endpoint of each interval. Right, this first interval, here's your right endpoint. Second interval, here's your right endpoint, all the way to your last interval, where your right endpoint would be b. Plug each one of those into your function, add up all of your outputs, and then multiply by the delta x. That's the length of each interval. And that'll give you the right-hand Riemann sum. Now, the left-hand Riemann sum is similar, but it's just using the left endpoints. Right, notice the only difference is, instead of going from x1 up to xn, right, looking at our interval here, instead of using the right endpoint of each interval, we're going to use the left endpoint of each interval. So the left endpoint of this first interval would be x0. The left endpoint of the second interval would be x1, etc. So the left-hand Riemann sum ends up being f of x0 times delta x plus f of x1 times delta x, all the way up to the left endpoint of the last interval. So if our last interval is here, the left endpoint would be x sub n minus 1. So the height of that last rectangle would be f of x sub n minus 1. If we go back to this first example here, this is exactly what we were doing. Here, let's see, the height of this box was f of 0 times the base of the box was 1. In this second rectangle, the height of the box was f of 1. We multiplied that by the base, which was again 1. And finally, the height of this last rectangle was f of 2 times the base, which was again 1. Right, so in this example here, what we were doing is we were finding the left-hand Riemann sum with 3 rectangles, so our n would be equal to 3. Okay, and again, the base of each rectangle is the same, it's delta x, so we can factor this delta x out in front and have delta x times f of x0 plus f of x1 all the way down the line to f of xn. And we could write that again using summation notation by saying it's delta x on the outside times f of x sub something. Right, we use I as a placeholder, where I is going to start at, our first index is 0, and it goes all the way up to our last, n minus 1, sorry, it should have been n minus 1 there, up to our last index of n minus 1. Right, you don't really need to know summation notation yet, but it's good to be familiar with it. And in the next video, we'll see some more examples of computing Riemann sums using these definitions.